Let's look at the history of the discovery of the subatomic particles of atoms. And the very first particle that was discovered was the electron in 1897 by an English scientist by the name of J.J. Thomson. And Dr. Thomson, he put together this cathode ray tube, is what he called it. So he had this glass container blown into the shape, and then he filled it with a gas, and he ran a current from one side to the other, and he had a luminous plate in here, and he was able to, after he turned on the electricity, he called these his cathode rays, and he noticed that every single element had these cathode rays. So he did an experiment, and you can watch a YouTube video that I have right after this video and see the cathode tube in action. But basically, he took a magnet and he put the magnet, the negative side, close to the cathode ray, and he saw that the cathode ray would bend up, showing that these cathode rays did have a negative charge. And then he could take the magnet and have the positive side go, and the cathode ray would dip down. And so he's able to prove that this particle had a negative charge and that every element had it. And later on, instead of calling it cathode rays, he called them electrons. Now, what you're really seeing with this cathode ray is not the electrons themselves, but instead evidence that the electrons were there. Kind of like when you walk through the snow and you look behind you, you can see your footprints. That's what's happening here. The electrons go by and illuminates the plate, and so you really just see the tracks that the electron made. All right, the scientist that quantified the charge of an electron was Robert Millikan. And this is his lab here. I just find it fascinating to see his working conditions and what he had. I also find it fascinating the experimental devices that they used to help them make their discoveries. But Robert Millikan, he took and he sprayed oil drops into his little oil drop experiment. There was a electromagnetic plate. We had negative charges here. We had positive charges here. And the oil drops were charged with electrons, and they fell through this hole in the middle. And it was small enough that one drop at a time could go through, so that he could just look and see what was happening to the drop. And these charged drops of oil, some of them hovered in midair, some just fell slowly, and some were actually repelled and went backwards against the flow of gravity. And that's because of the negative charge of this plate here. And through a lot of math and through recording the time of it dropping, he was able to quantify that, yes, the charge was a negative charge for this electron, but he quantified it as a 1.6 times 10 to negative 19 coulombs. And so this is a really, really small amount of charge. And it does have a negative sign, meaning that it's a negatively charged particle. Later on, when the proton was discovered, the proton was discovered to have a charge of a positive 1.6 times 10 to the negative 19 coulombs. And so I just find that fascinating. It has the exact same charge, or exact same amount of charge, but then just opposite sign. Because they both have the same amount of charge, just to make things easier, we say that an electron has a charge of -1 and a proton has a charge of +1, because it's the same value, but just oppositely charged. So the quantified charge of the electron occurred in 1909. All right, so Thomson, who was the original discoverer of the electron, wanted to put together some sort of atomic model, because if there's a negative particle, then there must be a positive particle. And he came up with what's called the plum pudding model. Now, he was British, and so British, instead of saying plum cake, they say plum pudding. So here's a plum pudding right here. To me, it looks like a raisin cake, but this is plum pudding. And so the plums are the negative little charges, and then the cake part is the positive charge. So this is what Thomson imagined in his mind, that there's a positive particle in opposition to his negative electron. So the next scientist we're going to talk about wanted to either prove or disprove Thomson's plum pudding model. And so this was Ernest Rutherford in 1911. He came up with what he called the gold foil experiment. So he pounded a really thin piece of gold that was just 1 or 2 atoms thick, and then he shot alpha particles at it. Now, an alpha particle is a radioactive particle and it's positively charged. And so to control where it's going to come out of, it's kept in this metal block with just one opening so that this alpha particle can come out of that one opening, and so Rutherford could aim it, so to speak, at the gold foil. And so he aimed it at the gold foil. Then he had a, a, a screen that would light up when the alpha particles hit it, and then he could sit and count all the little flashes of light to figure out what these alpha particles were doing. And he found that most of the alpha particles went straight through, but some were deflected to the side or directly right back at him. And here's his famous quote. He says, "It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." So he compared it to firing a bullet at a piece of tissue paper and having the bullet bounce back. So this was really shocking to him. And so from this experiment, he figured out that an atom is mostly empty space. So you can see right here that the alpha particles go uh, straight through, missing the nucleus of the gold atoms. And we find that the atom is mostly empty space. And Rutherford said that when the alpha particles are deflected, then that means that those alpha particles are hitting that nucleus and then bouncing off, kind of like what's depicted here. And if the link is working, there's a little video here of Rutherford's gold foil experiment. All right, so the Rutherford atom in 1911, we have a positive nuclear core with electrons outside of it. The Bohr atom, uh, Bohr studied electrons, and his atomic model is important because it shows that the electrons are certain distances from that nucleus. And I actually don't like this picture. The nucleus should be smaller. So that nucleus is really, really large. I would say that it's just a little dot there, okay, for the nucleus. That's probably even too large. So the nucleus is really, really small, and the electrons are outside the nucleus. And Bohr's atom is often called the planetary model, with the electrons going around the nucleus just like the planets go around the sun. All right, so Rutherford did find the positive particle that was found in that nucleus, and he called it the proton. And again, we know that its charge is a +1. It's the exact opposite of that electron. Rutherford's student, James Chadwick, he spent a lot of time trying to find the neutron, another heavy particle that was found to be in the nucleus. And it took 13 years to discover that because the neutron doesn't have a charge. All right, so here's a chart. There's a chart in your packet, and it may or may not match up, so make sure you pay attention. My chart starts out with the electron, and then goes to proton and neutron. And I did put their real masses here in grams, just so you could see how heavy these are, but these are not important. You don't even need to write these down. I just wanted you to see what the real masses are. And let's take a look at them. So if you look, the electron is 9 times 10 to the negative 28 grams. So very, 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 very small. Look at the proton in comparison. We see that the proton is much larger, 2,000 times larger, because it's 10 to the negative 24th. And now let's compare the neutron to the proton. So we can see that the neutron and the proton are very similar, but the neutron is just slightly bigger. So the two that are about the same size, we say that they have a mass of 1 atomic mass unit. So AMU is atomic mass unit. So scientists try to abbreviate it by using just a U, but it never really caught on. So we still use AMU for the unit. So if you go into a college class and they do use a U for atomic mass unit, just know that they're actually doing what they should be doing. So we say a proton has a mass of 1 atomic mass unit, and so does a neutron. Chemists tend to be a little lazy, and so because these are the same size, it just makes our lives easier but by saying that they have a mass of 1. Let's look at the electron. Notice the electron does have a mass, but in comparison with the proton and neutron, it is so small, so we say it has an atomic mass unit of 0. Let's go ahead and look at the charge. So we already said the charge of an electron is a -1, and the proton is equal in magnitude but opposite in charge, so a +1, and a neutron has a 0 charge. And over here on the purpose, I just put what each of these subparticles, what their importance is to the atom. So electrons is the source of our electricity. We will talk later on in the year about the electromagnetic spectrum that the electron does. And the electron gaining and losing electron causes chemical bonding. And so we will spend a lot of time talking about electrons with chemical bonding later on in the year. Let's look at the proton. The proton determines what element you have. So when you look on a periodic table and there's a big number, a source right by the symbol of the element, that is called the atomic number or the number of protons. And so you can look on the periodic table and see how many protons a certain element has. And let's look at the neutron. So the neutron is involved in the binding energy of the nucleus. So if you can imagine, if you have a whole bunch of positive charges in there, those positive charges are not going to want to be by each other. And so really look at the neutron kind of as a buffer there to keep those positive charges kind of separate from each other. And like I said, it is involved in the binding energy. And how it all works is more physics side and less chemistry side. But if you're interested in that, go ahead and do some independent research on your own if you're interested in binding